Hello, in this lecture we'll answer on two questions. In the first question, we'll find out the area of this rectangle ABCD that blocks this circle, and in the second question, we'll find out the area of this trapezoid ABCD. So we'll start with the first question. In the drawing, we have rectangle ABCD. This circle is inscribed by rectangle ABCD, or rectangle ABCD blocks this circle. In addition, remember that this is called EF, that is equals to 12 units in its length. This is line segment FG, that is equals to 10 units. Again, our mission is to find out the area of this rectangle ABCD. So first of all, we know that all the angles inside any rectangle are right angles. So this angle is a right angle. We will define the length of this rectangle ABCD as AB. And we will define the length of rectangle ABCD as AD, or DA. We define the radius of this circle as R. Point M is the point of tendency of tangent DC with this circle. Point E is the point of tendency of tangent DA with this circle. And finally, point N is the point of tendency of tangent AB with this circle. In the next step, we will join points O and N together by a straight line. Point O is the center of the circle, point N is the point of the circle itself, therefore ON is the radius of this circle that is equals to R according to our definition. The radius ON that is equals to R, the radius ON is drawn to point N, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NO. If AB is perpendicular to NO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and M together by a straight line. OM is of course the radius of this circle that is equals to R. So the radius OM that is equals to R, the radius OM is drawn to point M, that is the point of tendency of tangent DC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent DC will be perpendicular to the radius MO. If DC is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the sum rule, rule 1. In the next step, we join points O and E together by a straight line. OE is of course the radius of this circle that is equal to R. The radius OE is drawn to point E, that is the point of tendency of tangent DA with this circle. Whenever you have a radius that is drawn to the point of tendency, then tangent DA will be perpendicular to the radius EO. If DA is perpendicular to EO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the sum rule, rule 1. By doing this construction, we created the small quadrilateral DMOE. Inside the small quadrilateral DMOE, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4-piece angle, in total they must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this 4-piece angle must be equal to 90 degrees in its size. In the next step, we'll focus on the lower quadrilateral EO and A. In the lower quadrilateral, we have 1, 2, 3 right angles. The sum of three right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees, according to the symbol that said that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So, the big angle MON is equal to 90 degrees plus 90 degrees, that is 180 degrees. So, I write it down. Angle MON is equal to 180 degrees in its size. And you know that any angle that is equal to 180 degrees in its size, it is defined as a straight line. Therefore, line 7 MON is a straight line. If line 7 MON is a straight line, then MN is also a straight line. So actually, MN is a straight line that touches the circle at 2 points, point M and point N. And therefore, MN is a chord MN passes through point O, that is the center of the circle. Actually, the 3 points M, O, and N, they are located on the same straight line. And therefore, MN must pass through point O, that is one of the 3 points M, O, and N. So the straight line MN must pass through point O, that is the center of the circle. So MN is a chord that passes for the center of the circle. And we know that any chord that passes through the center of the circle must be the diameter of the circle. Therefore, MN is the diameter of the circle. So MN is the diameter of the circle, so MN is the diameter, it is absolutely a straight line. So shape DMNA consists of 4 sides. 1, 2, 3, 4. And therefore shape DMNA is a quadrilateral. It is a quadrilateral with 4 right angles, and therefore shape DMNA must be at least a rectangle, if not a square, according to rule 5. Okay. So quadrilateral DMNA is 4 right angles, and therefore quadrilateral DMNA is a rectangle according to rule 5. So in rectangle DMNA, the opposite sides must be equal to each other. In rectangle DMNA, the opposite sides must be equal to each other. So write it down that the big quadrangle DMAN is a rectangle. So in the big rectangle DMNA, the opposite sides must be equal to each other. That is to say, side MN must be equal to the opposite side DA. MN equals to the opposite side DA. But according to our definition, side DA of rectangle ABCD is the width of rectangle ABCD. So you can write it that DA is the width of rectangle ABCD. From one side, but from the other side, we have already found out that MN is the diameter of the circle. Here, MN is the diameter of the circle. So you can write here that MN is the diameter of the circle. In the next step, we will extend the radius EO that is equal to R. We will extend the radius EO by a straight line until it touches the circle. And we will define the touching point of the extended radius EO with this circle. This point is point L. So actually, we extended the radius EO, that is a straight line by straight line. When you extend a straight line by straight line, the result must be a straight line. Therefore, EL must be a straight line. EL is a straight line that touches the circle at 2 points, point E and point L. And therefore, EL is a chord. EL is a chord that passes from point O. Why EL passes from point O? Because we extended the radius EO from point O until it touches the circle at this point, point L. Therefore, EL absolutely passes from point O, that is the center of the circle, and we know that any chord that passes through the center of the circle must be the diameter of the circle. Therefore, EL is the diameter of the circle. So write down that EL is the diameter of the circle. So I can write here in the long equation that EL is the diameter of the circle. EL is the diameter of the circle. And from this long equation, EL equals to the diameter equals to MN equals to DA equals to the width. We will derive that EL is the width of rectangle ABCD. EL is the width of rectangle ABCD. In the next step, we will join points F and L together by a straight line. By joining points F and L, we create peripheral angle EFL. This is peripheral angle EFL that subtends on EL, that is the diameter of the circle, and we know that any peripheral angle that subtends on the diameter of the circle must be equal to 90 degrees in its size, according to rule 7. So if it's speaking on rule 7, according to rule 7, if a peripheral angle subtends on the diameter of the circle, then it must be equal to 90 degrees in its size. So in the drawing, we have a circle. AB is the diameter of this circle. this is peripheral angle ACB that subsets on AB, that is the diameter of this circle, and therefore according to this rule 7, the size of peripheral angle ACB must be equal to 90 degrees, or peripheral angle ACB must be equal to 90 degrees in size. So we can implement rule 7 in our drawing. One code in our drawing, we have peripheral angle EFL that subtends on EL, that is the diameter of the circle. Therefore, peripheral angle EFL must be equal to 90 degrees in size according to rule 7. In the next step, we define angle LEF. This angle is alpha. So, in the right triangle EFL, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. In the next step, we will extend the diameter EL by straight line until it touches side CB of rectangle ABCD. Okay, again, we will extend the diameter EL of this circle by straight line until it touches side CB, this side CB of rectangle ABCD. And we will define the touching point of the extended diameter EL with side CB. This point is point T. ET is definitely a straight line because we extended the diameter EL, that is absolutely a straight line, by straight line. When we extend the straight line by straight line, the result must be a straight line. Therefore, ET must be a straight line. So by doing this construction, we created quadrilateral ETBA. Inside this quadrilateral ETBA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So inside the big quadrilateral ETBA, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we know to the big quadrilateral ETBA is a rectangle because it has 4 right angles. So quadrilateral ETBA is a rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ETBA, side ET must be equal to the opposite side AB. So write it down. In rectangle the big rectangle ETBA, side ET must be equal to the opposite side AB. Because again, in rectangle ETBA, side ET equals to side AB, the opposite side AB. But according to our definition, AB is the length of rectangle ABCD. So we can write that AB is the length of rectangle ABCD. And for this equation, ET equals to AB equals to the length of rectangle ABCD. We will derive that ET is also the length of rectangle ABCD. So in conclusion, we found out that ET is the length of rectangle ABCD, and EL is the width of the same rectangle ABCD. EL is the width of rectangle ABCD. In the next step, we'll focus on the big right triangle ETG. On the big right triangle ETG, this angle equals to alpha, this angle equals to 90 degrees, therefore this front missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. It is very easy to see from the drawing that the big right triangle ETG is similar to the small right triangle ELF according to angle similarity rule. Anyway, I will explain why those two right triangles are similar to each other. That is to say, why the big right triangle ETG is similar to the small right triangle ELF. First of all, this is angle E. That is a common angle that belongs to both triangles. Angle E belongs to the right small triangle ELF, and angle E definitely belongs to the big right triangle ETG. So we can write down that angle E equals to itself is a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So if you found out that all the figures of the big right triangle ETG are correspondingly equal to all the figures of this right small triangle ELF, and therefore those two right triangles are similar to each other according to angle similarity rule. So write it down. If you found out that the big right triangle ETG is similar, this is the sign of similar, to the small right triangle ELF, according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side ET of the big right triangle ETG over side EF of the small right triangle ELF is equal to side EG of the big right triangle ETG over side EL of the small right triangle ELF. So repeat again. From the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side ET of the big right triangle ETG over side EF of the small right triangle ELF is equal to side EG of the big right triangle ETG over side EL of the right small triangle ELF. ET is the missing side, so we leave it as it is. Over EF. EF equals to 12 units in its length according to what is given us the question. And it is equals to EG. EG in total equals to 12 plus 10, that is 22. Over EL. EL is the missing side, so we leave it as it is. So in total, we actually found out that ET over 12 equals to 22 over EL. Here, we will first multiply this equation, and we get that ET times EL is equal to 22 times 12. So ET times EL is equal to 22 times 12. 22 times 12 is 264. So in total, if we found out that ET times EL equals to 264. What we already found out that ET is the length of rectangle ABCD and EL is the width. So we substitute ET by the length of rectangle ABCD and we substitute EL by the width of rectangle ABCD. And it is equal to 264. So the length of rectangle ABCD times the width is equal to 264 square units. What is the length times the width? The length times the width of any rectangle is the area of the rectangle. Therefore, the length of rectangle ABCD times the width of rectangle ABCD is equal to the area of rectangle ABCD. So if we found out that the area of rectangle ABCD is equal to 264 square units. And that is the answer to the first question. I'll repeat again. We should found out that the area that we are looking for in this question, that is the area of this rectangle ABCD, is equal to 264 square units. So we finished with the first question. In the next step, I will present to you the second question and we will solve the second question of this lecture. In the second question, our task is to find out the area of this trapezoid ABCD. It is given us the question that side AB equals to line segment AP, PD equals to DC, line segment BQ equals to 4 units in its length, line segment QC equals to 9 units in its length. This is angle PQC, that is a right angle. Those two angles are both right angles. Again, our task is to find out the area of this trapezoid ABCD. So first of all, because of the fact that AB is equal to AP according to what is given us in the question, we will define the length of side AB as A, that is to say side AB equals to A units in its length according to our definition. So if the length of side AB is A, then AP must be also equal to A because of the fact that they are equal to each other in their lengths. Likewise, it is given the question that PD equals to DC. So we define the length of PD as B. If the length of PD is B, then the length of DC must be also equal to B because they are equal to each other according to what is given in the question. In the next step, we join points B and P together by a straight line. And we join points P and C together by a straight line. By joining points B and P, we created the right small triangle APB. The right small triangle APB is also an associated triangle. Why? Because AB equals to AP. So the right small triangle is at the same time simultaneously a right triangle is also an associated triangle. We have the rule that in front of equal sides in the triangle there are equal angles. So in front of those two equal sides we have those two angles that must be also equal to each other on their sides because they are located in front of those two equal sides. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other. So we know that the sum of the angles in any triangle is equal to 180 degrees. It is true in any triangle, therefore it's also true in the right and associated triangle, triangle ABP. So which angles we have in the right and associated triangle, triangle ABP? We have this angle that is a right angle, plus alpha that is plus 2 alpha. In total, the sum of those three angles must be equal to 180 degrees. Here we subtract 90 degrees from this equation, and we get that 2 alpha equals to 180 degrees minus 90 degrees. It is 90 degrees, so 2 alpha equals to 90 degrees. Here we divide this equation by 2, and finally we get that alpha, the missing angle alpha equals to 90 degrees over 2, that is 45 degrees. So actually, this is angle alpha, the size of this angle alpha is 45 degrees. The size of this angle alpha is also 45 degrees. So we can conclude from this specific example that any right angle that is also an associated triangle, any right angle that is also an associated triangle, will have always the same three angles. One angle will be equal to 90 degrees, and the other two angles, they must be equal to 45 degrees each of them. Therefore, in this right and associated triangle, triangle PDC, this angle is right angle, it is equal to 90 degrees in its size. So the size of those two angles, each of them must be equal to 45 degrees in its size. You don't have to repeat on the same proof in this right and associated triangle PDC, because the proof is exactly the same proof that we proved in this right and associated triangle APB. So it will be a waste of time. So this angle equals to 45 degrees, and this angle also equals to 45 degrees, because of the fact that the right triangle PDC is also an associated triangle, because of the fact that PD equals to DC according to what is given in the question. So those two angles, each of them is equal to 45 degrees in the sizes, in its size. We know that AD is one side of trapezoid ABCD, therefore it is absolutely a straight line. So if we focus on the right side of the straight line AD at point P, here the sum of the angles must be equal to 180 degrees, according to rule 3 that states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the right side of the straight line AD at point P? We have this angle that is 45 degrees plus this angle that is 45 degrees. In total they are equal to 90 degrees. So 90 degrees plus the size of this third missing angle, in total they must be equal to 180 degrees according to rule 3. Therefore this third missing angle must be equal to 90 degrees in its size. Why? Because 90 degrees plus 45 degrees plus 45 degrees, it is equal to 180 degrees. That is the sum of the angles on the right side of the straight line AD at point P, according to rule 3. So we define the small angle BPQ as alpha. So the missing angle QPC, this is the missing angle, must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees minus alpha plus alpha is equal to 90 degrees. That is the size of the big angle BPC. So the missing angle here must be equal to 90 degrees minus alpha. You can see it from the drawing itself that 90 degrees minus alpha plus alpha is equal to 90 degrees. That is the size of the big angle BPC. So in the right angle PQC, this angle equals to 90 degrees, this angle equals to 90 degrees minus alpha. Therefore, this third missing angle must be equal to alpha. Why? Because alpha plus 90 degrees minus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. We know that BC is one side of trapezoid ABCD, therefore it is absolutely a straight line. So if we focus on the left side of the straight line BC at point Q here, the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have at the left side of the straight line BC at point Q? We have this angle that is a right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So in the right small triangle BQP, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. So in the next step, we will prove that the green right small triangle BQP is similar to the big right triangle PQC. So why those two right triangles are similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So I should prove that all the angles of the big right triangle PQC are correspondingly equal to all the angles of the green small right triangle PBQ. And therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down, and if you found out that the big right triangle PQC is similar, this is the sign of similar, to the small right triangle PBQ, to the small green right triangle PBQ, according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. But first of all, PQ is a common side that belongs to both triangles. PQ definitely belongs to the small green triangle PBQ, and PQ also belongs to the big right triangle PQC. So PQ is a common side that belongs to both triangles. So from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that PQ of the big right triangle PQC over BQ of the small right triangle PBQ is equal to QC of the big right triangle PQC over PQ of the small right triangle PBQ. So repeat again, from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side PQ of the big right triangle PQC over side BQ of the small right triangle PBQ is equal to side QC of the big right triangle PQC over side PQ of the small right triangle PBQ. PQ is the missing sides of vertices over BQ. BQ equals to 4 units in its length according to what is given as the question. And it is equals to QC. QC equals to 9 units, also according to what is given as the question, over PQ. So PQ is the missing sides of vertices. So in total, we actually found out that PQ over 4 equals to 9 over PQ. Here we will cross multiply this equation and we will get that PQ times PQ, that is PQ squared, is equal to 9 times 4, that is 36. So PQ squared equals to 36. Here we'll take a root out of this equation and finally we get that the missing side PQ is equal to the square root of 36, that is 6. So the missing side PQ equals to 6 units in its length. So I write it down in the drawing. This is the missing side PQ that is equal to 6 units in its length. In the next step, we will implement the Pythagoras theorem on the big right triangle BPC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is a variation for Pythagoras theorem. The hypotenuse in the big right triangle PBC is BC, therefore the square of the hypotenuse is BC squared, and BC squared must be equal to BP squared plus PC squared. So if you found out that according to the Pythagoras theorem, it is right big triangle PBC, BC squared, that is the square of the hypotenuse, equals to BP squared plus PC squared. The hypotenuse BC equals to 9 plus 4, that is 13 units. So BC squared is 13 squared, that is 169. And it is equals to BP squared. What is the value of BP squared? In order to find out the value of BP squared, we will implement the Pythagoras theorem on the small right triangle BAP. And on the small right triangle BAP, according to the Pythagoras theorem, we will get that A squared plus A squared equals to PB squared. So BP squared equals to A squared plus A squared, that is 2A squared. So BP squared equals to 2A squared plus PC squared. What is the value of PC squared? In order to find out the value of PC squared, we will implement the Pythagoras theorem on the right triangle, triangle PDC. According to the Pythagoras theorem on the right triangle, triangle PDC, B squared plus B squared equals to PC squared. So PC squared in total, it is B squared plus B squared, that is 2B squared. So PC squared is 2B squared. So in total, we should find out that 169 equals to 2A squared plus 2B squared. So 169 equals to, here we take out 2 as a common factor from those two expressions. So inside the brackets we left only with A squared plus B squared. So in total we should find out that 169 equals to 2 times A squared plus B squared. Here we will divide this equation by 2 and finally we get that A squared plus B squared, A squared plus B squared equals to 169 over 2. So repeat again, we shall find out that a squared plus b squared equals to 169 over 2. Our task is to find out the area of this trapezoid ABCD. So what is the area of trapezoid ABCD? Actually, the area of trapezoid ABCD must be equal to the sum of the areas of the three components that trapezoid ABCD consists of. Trapezoid ABCD consists of, the first component is the right small triangle ABP, the second component is the right big triangle PBC, and the third component is the right triangle PDC. So the sum of the areas of those three components must be equal to the area of trapezoid ABCD. So I'll write it down. The area of trapezoid ABCD equals to the area of the first component, that is actually the area of the right small triangle ABP, plus the area of the second component, that is the area of the big right triangle PBC, plus the area of the first component, that is the area of the right triangle PDC. So repeat again, I shall find out that the area of trapezoid ABCD equals to the sum of the areas of the three components that it consists of. That is to say, it is equals to the area of the small right triangle ABP plus the area of the big right triangle PBC plus the area of the right triangle PDC. So the sum of the areas of the three components will give us the area of the trapezoid ABCD. So we calculate the area of each component separately, and the sum of the areas of the three components will give us the area of trapezoid ABCD. So the area of the first component is the area of the right small triangle ABP. We know that the area of any triangle equals to the base of the triangle times the height over 2. So what is the area of the small triangle ABP? It is equal actually to the base of the triangle, that is AB, times the height, that is AP over 2. AB is A, AP is also A, so it is A times A, that is A squared over 2. So in total, we shall find out that the area of trapezoid ABP, the small triangle ABP, is equal to A squared over 2, plus the area of the second component, that is the area of the big right triangle PBC. What is the area of this big right triangle PBC? It is equal to the base of the triangle, that is BC, times the height, that is QP, over 2. Repeat again, the area of the big right triangle PBC is equal to the base BC times the height QP over 2. QP is the height because it creates 90 degrees with the base BC. Those two angles are right angles. And finally, plus the area of the third component, that is the area of this right triangle PDC. The area of this right triangle PDC equals to the base DC times the height DP over 2. The base DC is B, the height DP is also B, divided by 2. So it is B times B, that is B squared over 2. So in total, the area of this right triangle PDC is B squared over 2. So here we have A squared over 2 plus B squared over 2 is A squared plus B squared over 2. The area of the big right triangle PBC is equals to BC. BC in total equals to 4 plus 9, that is 13. times QP. QP equals to 6 divided by 2. So in total, we actually found out the derivative of the ABCD equals to a squared plus b squared over 2 plus 13 times 6 over 2. We have already found out that a squared plus b squared equals to 169 over 2. Therefore, we substitute a squared plus b squared in this expression by 169 over 2, and we have to divide it by 2 again. So in total, this expression equals to 169 over 2 times 2 plus 13 times 6 over 2. 13 times 6 over 2 is 6 over 2 is 3, and 3 times 13 is 39. So in total, this expression equals to 39. So in total, the trapezoid ABCD equals to 169 over 2 times 2 is 4 plus 39. Here we will multiply 39 by 4 and then we divide it by 4 in order to have a common factor with this number. And we get that in total the numerator will have 169 plus 39 times 4 is 156 divided by 4. 169 plus 156 is 325 divided by 4. 325 over 4 is 81.25 square units. So we have found out that the area that we are looking for in this question, that is the area of trapezoid ABCD, it is equal to either 325 over 4 square units, so in terms of numbers, the area of trapezoid ABCD is equal to 81.25 square units. So we finish with the second question. In the next step, I will summarize the lecture. We'll start with the first question, of course. In the first question, our task is to find out the area of this rectangle ABCD. So in the drawing, we have a rectangle ABCD that blocks this circle, or this circle is described by rectangle ABCD. In addition, you know that this is called EF, that is equals to 12 units in its length. This is line segment FG, that is equals to 10 units. And again, our mission is to find out the area of this rectangle ABCD. So first of all, we know that all the angles inside the rectangle are right angles. So this is a rectangle, and we defined the length of rectangle ABCD as AB, and the width as DA. And the length times the width is of course the area of any rectangle, and especially the area of rectangle ABCD. Okay. We defined the radius of this circle as R. We join points O and N together by straight line. Point O is the center of the circle, point N is the point of the circle itself, therefore ON is the radius of this circle that is equal to R. The radius ON that is equal to R is 1 to point N, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius AO, to the radius NO. If AB is perpendicular to NO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and N together by straight line. ON is of course the radius of, we join points O and N together by straight line. OM is the radius of this circle that is equal to R. The radius OM is down to point M, that is the point of tendency of tangent DC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent DC will be perpendicular to the radius MO. If DC is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. In the next step, we join points O and E together by straight line. OE is of course the radius of this circle that is equal to R. the radius OE is drawn to point E, that is the point of tendency of tangent DA with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent DA will be perpendicular to the radius EO. If DA is perpendicular to EO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the sum rule, rule 1. By doing this construction, you can deduct quadrilateral DMOE. Inside quadrilateral DMOE, we have 1, 2, 3, right? 1, 2, 3 right angles. The sum of right angles is 270 degrees. So 270 degrees plus the size of this four facing angle. In total, they must be equal to 360 degrees, according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this four facing angle must be equal to 90 degrees in its size. Likewise, in the small quadrilateral EO and A, we have 1, 2, 3 right angles. The sum of right angles is 270 degrees. So 270 degrees plus the size of this four facing angle, in total it must be equal to 360 degrees, according to the sum rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this four facing angle must be equal to 90 degrees in its size. So if we found out that the big angle MON is equal to 90 degrees plus 90 degrees, that is 180 degrees. So again, the big angle MON is equal to 180 degrees. And we know that any angle that is equal to 180 degrees in its size, it is defined as a straight line. So line 7 MON is a straight line. If line 7 MON is a straight line, then MN is also a straight line. MN is a straight line that touches the circle 2 points, M and N. Therefore, MN is a chord. MN is a chord that passes through point O, that is the center of the circle, and we know that any chord that passes through the center of the circle must be the diameter of the circle. So we found out in conclusion that MN is the diameter of the circle. So MN is the diameter, it is absolutely a straight line. Therefore this shape DMNA consists of 4 sides, 1, 2, 3, 4. And therefore, shape DMNA is a quadrilateral that has 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be a rectangle if not a square. So we relate to the big quadrilateral DMNA as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in the big rectangle DMNA, side MN must be equal to the opposite side DA. Repeat again, in the big rectangle DMNA, side MN must be equal to the opposite side DA. But DA, according to our definition, is the width of rectangle ABCD. So we wrote down here that DA is the width of rectangle ABCD, and we just tried to find out that MN is the diameter of the circle. So we can write here that MN is the diameter of the circle. In the next step, we extended the radius EO by straight line until it touches the circle. We define the touching point of the extended radius EO with this circle. This point is point L. EO as a radius, it is absolutely a straight line. When you extend a straight line by straight line, the result must be a straight line. So the result EL must be a straight line. So EL is a straight line that touches the circle at 2 points, E and L. Therefore EL is a chord that passes through point O. EL definitely passes through point O because we extended the radius EO by a straight line. Therefore EL definitely passes through point O. So EL passes through point O. That is the center of the circle, and we know that any chord that passes through the center of the circle must be the diameter of the circle. Therefore EL is the diameter of the circle. So we can write here that EL is the diameter of the circle, and from this long equation EN equals to the diameter equals to MN equals to DA equals to the width, we will derive that EL is also the width of rectangle ABCD. Okay. In the next step, we join points L and F together by straight line. By joining points L and F, we can get peripheral angle EFL. Peripheral angle EFL subtends on EL, that is the diameter of the circle, and according to rule 7, any peripheral angle that subtends on the diameter of the circle must be equal to 90 degrees in its size. Therefore, peripheral angle EFL must be equal to 90 degrees in its size according to rule 7. So in the next step, we define this angle LEF as alpha. So So in the right triangle ELF, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third angle must be equal to 90 degrees minus alpha. 1 plus 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. In the next step, we extended the diameter EL by a straight line until it touches side CV of rectangle ABCD at this point. So we define the touching point of the extended diameter EL with side CB. This side is this point is point T. So EL is a diameter, it is absolutely a straight line. When you extend a straight line, by straight line the result is a straight line. So therefore the result ET must be also a straight line. So in quadrilateral ETBA we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total it must be equal to 360 degrees, according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So inside the big quadrilateral ETBA we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we refer to the big quadrilateral ETBA as a rectangle. So quadrilateral ETBA is a rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So in the big rectangle ETBA, side ET must be equal to the opposite side AB. So repeat again, in the big rectangle ETBA, side ET must be equal to the opposite side AB. But according to our definition, AB is the length of rectangle ABCD. So we can write here that AB is the length of rectangle ABCD. And from this equation, ET equals to AB equals to the length. We will derive that ET is also the length of rectangle ABCD. And we already found out that EL is the width of rectangle ABCD. In the next step, we focus on the big right triangle ETG. On the big right triangle ETG, this angle equals to alpha, this angle equals to 90 degrees, therefore this third missing angle must be equal to 90 degrees minus alpha. Y equals 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. So in the next step, we prove that the big right triangle ETG is similar to the small right triangle, triangle ELF. So why those two right triangles are similar to each other? First of all, this is angle E. It is a common angle that belongs to both triangles. Angle E belongs to the right small triangle ELF, and angle E also belongs to the big right triangle, triangle ETG. So we can write down that angle E equals to itself as a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we should prove that all the angles of the big right triangle ETG are correspondingly equal to all the angles of the right small triangle ELF. And therefore those two right triangles are similar to each other according to angle similarity rule. So if it again, if we found out that the big right triangle ETG is similar, this is the sign of similar, to the small right triangle, triangle ELF, according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side ET of the big right triangle ETG over side EF of the small right triangle ELF is equal to side EG of the big right triangle ETG over side EL of the small right triangle ELF. If it again, from the fact that those two right triangles are similar to each other, we will derive that side ET of the big right triangle ETG over side EF of the small right triangle ELF is equal to side EG of the big right triangle ETG over side EL of the small right triangle ELF. ET is the missing side, so we leave the cities over EF. EF equals to 12 units in Islam, we want to know what is given as the question. And it is equals to EG. EG in total equals to 12 plus 10, that is 22. Over EL. EL is the missing side, so we leave the cities. So in total, we should find out that ET over EF equals to EG over ET over 12 equals to 22 over EL. So here we cross multiply this equation and finally found out that ET times EL equals to 22 times 12. So ET times EL equals to 22 times 12. 22 times 12 is 264. So in total we found out that ET times EL equals to 264. But we already found out that ET is the length of rectangle ABCD and EL is the width of rectangle ABCD. So we can substitute ET by the length of rectangle ABCD and we substitute EL by the width of rectangle ABCD. So in total we found out that the length of rectangle ABCD times the width of rectangle ABCD is equal to 264 square meters. The length of rectangle ABCD times the width is the area of rectangle ABCD. So in total we found out that the area that we are looking for in this question, that is the area of rectangle ABCD, is equal to 264 square meters. So repeat again, we found out that the area of this rectangle ABCD is equal to 264 square meters. So we finish with the first question. In the next step, I presented to the second question and we solve the second question of this lecture. In the second question, our task is to find out the area of this trapezoid ABCD. So in the drawing, we know that side AB equals to side AP, side PD equals to side DC, PQ equals to 4 units in itself, QC equals to 9 units in itself. Again, our mission is to find out the area of this trapezoid ABCD. So first of all, AB equals to AP according to what is given as the question. So if we define the length of AB as A, then the length of AP must be also equal to A because they are equal to each other. Likewise, PD equals to DC according to what is given as the question. So if we define the length of PD as B, then the length of DC must be also equal to B because they are equal to each other according to what is given as the question. In the next step, we join points B and P together by side line. We join points P and C together by side line. By joining points B and P, we get the right small triangle ABP. In the right small triangle ABP, those two sides are equal to each other, and we have the rule that in front of equal sides in the triangle, there are equal angles. So in front of those two equal sides, we have those two angles that must be equal to each other. So if this is angle alpha, then this angle must be also equal to alpha because those two angles are equal to each other. And we know that the sum of the angles in any triangle is equal to 180 degrees. So in the right triangle ABP, 90 degrees plus alpha is equal to 180 degrees. In the right triangle ABP, 90 degrees plus 2 alpha equals 180 degrees. Here we subtract the 90 degrees from this equation and finally found out that 2 alpha equals to 180 degrees minus 90 degrees, that is 90 degrees. Here we divided this equation by 2 and finally found out that alpha equals to 90 degrees over 2, that is 45 degrees. So this is again alpha that is equals to 45 degrees in its size. This is also again alpha that is equals to 45 degrees in its size. So this is a right triangle that is also an associated triangle because AP equals to AB. So we can conclude from this example that in any right triangle that is also an associated triangle, we have always the same three angles. We have one angle that is a right angle, and the two other angles must be equal to 45 degrees each of them. Therefore, in this right triangle that is also an associated triangle, this angle is a right angle. Those two angles must be equal to 45 degrees in each of them. Triangle PDC is an associated triangle because PD equals to DC. So those two angles must be equal to 45 degrees each of them. So we know that AD is one side of trapezoid ABCD, therefore it is absolutely straight line. So if we focus on the right side of the straight line AD at point P, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles from one side of a straight line is equal to 180 degrees. So which angles we have at the right side of the AD at point P? We have this angle that is 45 degrees, plus this angle that is 45 degrees, in total they are equal to 90 degrees. So 90 degrees plus the size of this third missing angle, in total it must be equal to 180 degrees according to rule 3. Therefore this third missing angle must be equal to 90 degrees in its size. So why? Because 90 degrees plus 45 degrees plus 45 degrees, it is equal to 180 degrees. That is the sum of the angles on the right side of the straight line AD at point P according to rule 3. We define the small angle BPQ as alpha. Therefore, this missing angle QPC must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees. That is the size of the big angle BPC. So this angle must be equal to 90 degrees minus alpha. In the right big triangle PQC, this angle equals to 90 degrees minus alpha. This angle equals to 90 degrees. Therefore, this first missing angle must be equal to alpha. Why? Because alpha plus 90 degrees minus alpha is 90 degrees. And 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. BC is one side of trapezoid ABCD, therefore it is absolutely a straight line. So if we focus on the left side of the straight line BC at point Q, here the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have on the left side of BC at point Q? We have this angle that is the right angle, plus this missing angle, in total must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. So in the right small green triangle BPQ, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in a triangle. In the next step, we prove that the big right triangle PQC is similar to the small green triangle PQB. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. And finally, those two angles are both equal to alpha, therefore they are equal to each other. So we shall prove that all the figures of the big right triangle PQC are correspondingly equal to all the figures of the green small triangle PBQ. And therefore, those two right triangles are similar to each other according to angle similarity rule. So repeat again, we shall find out that the big right triangle PQC is similar to the small right triangle PBQ according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive, but first of all, side PQ is a common side that belongs to both triangles. Side PQ belongs to the green triangle PQB, and side PQ also belongs to the big triangle PQC. So from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side PQ of the big right triangle PQC or side BQ of the small right triangle PBQ is equal to side QC of the big right triangle PQC or side PQ of the small right triangle PBQ. So if again, from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side PQ of the big right triangle PQC or side BQ of the small right triangle PBQ is equal to side QC of the big right triangle PQC over side PQ of the small right triangle PBQ. PQ is the missing sides of relative cities, BQ is 4, QC is 9 over PQ. PQ is the missing sides of relative cities. So in total, we shall find out that PQ over 4 equals to 9 over PQ. Here we cross multiply this equation and finally found out that PQ times PQ is PQ squared, and PQ squared equals to 9 times 4, that is 36. So PQ squared equals to 36. We took out of this equation and finally found out that PQ equals to the square root of 36, that is 6. So this is the missing side PQ, that is equals to 6 units in its length. In the next step, we implemented the Pythagoras theorem on the right big triangle PBC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in the right the right big triangle PBC, BC is the hypotenuse, therefore the square of the hypotenuse is BC square, and BC square must be equal to BP square plus PC square. So repeat again, in the right big triangle PBC, according to the Pythagoras theorem, BC square, that is the square of the hypotenuse, equals to BP square plus PC square. The hypotenuse BC in total is 4 plus 9, that is 13. So BC is 13, therefore BC square is 13 squared, that is 169. BC square is 169, and it is equals to BP square. What is the value of BP square? In order to find out the value of BP square, we implement the Pythagoras theorem on the small right triangle PAB. According to the Pythagoras theorem in the small right triangle PAB, A square plus A square equals to BP square. So BP square in total equals to A square plus A square, that is 2A square. So BP square equals to 2A square plus PC square. So what is the value of PC square? In order to find out the value of PC square, we will implement the Pythagoras theorem on the right triangle PDC. According to the Pythagoras theorem on the right triangle PDC, B square plus B square equals to PC square. So PC square in total equals to B square plus B square, that is 2B square. So here PC square equals to 2B square. So in total we found out that 169 equals to 2A square plus 2B square. So 169 equals to, here we took out 2 as a common factor from those two expressions, so inside the brackets we left only with A square plus B square. So in total we found out that 169 equals to 2 times A square plus B square. Here we divided this equation by 2 and finally found out that a squared plus b squared equals to 169 over 2. Our task is to find out the area of this trapezoid ABCD. The area of trapezoid ABCD must be equal to the sum of the areas of the three components that trapezoid ABCD consists of. Trapezoid ABCD consists of three components. The first component is the right small triangle ABP, the second component is the right big triangle PBC, and the third component is the right triangle PBC. So the sum of the areas of those three components must be equal to the area of trapezoid ABCD. So again, the area of trapezoid ABCD equals to the area of the first component, that is the area of the small right triangle ABP, plus the area of the second component, that is the area of the big right triangle PBC, plus the area of the third component, that is the area of the right triangle PDC. The area of the first component, that is the area of the right small triangle ABP. This is the right small triangle ABP. The area of this right triangle ABP is equal to the base of the triangle times the height over 2. The base is AB times the height is AP over 2. AB is A, AP is also A, so it is A times A, that is A squared over 2. So in total, the area of this right triangle ABP is equal to A squared over 2. The area of the right triangle ABP is equal to A squared over 2. Plus the area of the big right triangle PBC. What is the area of this big right triangle PBC? It is equal to the base BC times the height QP over 2. BC in total equals to 4 plus 9, that is 13. Times QP, that is 6 over 2. Then again, the area of the right triangle PBC equals to the base BC times the height QP over 2. BC is 13, QP is 6 over 2. Plus the area of the third component, that is the area of this right triangle PDC. The area of the right triangle PDC equals to the base of the triangle, that is DC, times the height, that is DP over 2. DC is B, DP is also B, so it is B times B, that is B squared over 2. So total the area of the third component, that is the area of triangle PDC, the right triangle PDC is equals to B squared over 2. So A squared over 2 plus B squared over 2 is A squared plus B squared over 2. And we have here the area of the big triangle PBC is equal to 13 times 6 over 2. We have already found out that A squared plus B squared equals to 169 over 2. So we solved A squared plus B squared by 169 over 2, and we have to divide it by 2 again. So in total this expression equals to 169 over 2 times 2. 13 times 6 over 2 is equal to 6 over 2, that is 3 times 13. 3 times 13 is 39. So in total, the value of this expression is 39. 169 over 2 times 2 is 169 over 2 times 2 is 4. So it is 169 over 4 plus 39. Here we multiply 39 by 4 and then we divide it by 4 in order to have a common factor with this number. So in total, the numerator will have 169 plus 39 times 4, that is 156. So in total, in the numerator we have 169 plus 156, that is 325 divided by 4. 325 over 4 is 81.25. So in total, we found out that the area of this trapezoid ABCD is equal to either 325 over 4 square units. So in terms of numbers, the area of this trapezoid ABCD is equal to 81.25 square units. Okay, thank you very much.